And I handed you something here. This is a quiz to be turned in at the beginning of class next time. Can you all see that on there? It says it's a quiz.
Do at the beginning of class.
Do as in D-O instead of D-U-E.
What? Okay. Yeah, it's a math guy doing that. Do, D-U-E. All right, so I start off great here today.
Think about it and then come back and do it.
Do it, yeah.
Like, oh, do we just...
So at the beginning of next class, so what these are, if you look over here, we have our formulas, right, that we can use on tests. And some of these formulas over here on the side are formulas that, you know, we use them, but the question is like where they come from, right? In fact, all these formulas on this page, even the ones down here, formulas 21 through 29, are all formulas that you could actually derive yourself using trigonometric substitution. So what I want you to do is take formulas 16, 18, 19, and 20, and I want you to use trigonometric substitution to verify that these are true, all right, that these formulas are what they are. So you're gonna, now if you're like, how do I do this? Don't worry, I'm actually gonna do 17 to start class. So you'll kind of see how it's done. And then you do the rest. A little bit of advice to you on number 19, you're gonna have to mess with it algebraically. Like after you finish with the antiderivative, the algebra's a little weird. To make it look like that answer, you're gonna have to remember some stuff about logarithms and things like that. So see how it goes. And then on number 20, there's kind of a hard way and an easy way. The hard way is just to start from scratch and do the problem. The easy way is to realize that formula 19 and 20 are very close to one another. And if you just do something algebraically in the beginning, then you basically don't have to go and derive the whole thing again. I'll leave it at that, all right? See how it goes. If you need help on this, feel free to reach out, okay? All right, let's get going. So 6.3, the notes. So I told you that this section is kind of long and it's tough, kind of like the previous section, the trig integrals and trig sub. We're gonna spend the entire week on this section. All right. So today, what we're gonna do is we're gonna get preliminary things out of the way first. We need to make sure that there are certain things that we can do, we can handle. And once we get those out of the way, then we will say, okay, let's go do partial fractions. And our ultimate goal will be to try and get a problem to turn out like this preliminary stuff. And then we're like, oh yeah, we know how to do that, right? So that's the goal. So the first thing here is we're going to look at this formula 17, and we are going to see where it comes from. We are going to show that this is true, all right? So I'm about to verify formula 17. It says that if you take the antiderivative of 1 over u squared plus a squared du, that this is equal to 1 over a arctangent of u over a plus c, right? That's the formula. So question to you. What is the variable in this problem? What is the independent variable? U. U is the independent variable. How do we know that? du, okay? That means a in the problem is a constant, right? So u is like x has been, right? And a is just going to be some number we don't know, all right? So we're trying to find the antiderivative of this. Let's start here. Okay, so I'm trying to show this, right? I'm trying to show that this is true. So I'm going to start here. And the first thing I'm going to do is not going to seem very natural, but we have a way to handle this with trig sub if we've got our variable squared plus a constant squared, right? But we need it under a square root, don't we? Yes. So I'm going to write this underneath the square root. I'm going to write it as square root of this, but then all of that squared. See, that's not very natural, right, to want to look at it that way, but I can do that, right? And by doing it this way, now I can use a trig sub. So what would my trig sub be? What do you do when you have your variable squared plus the constant squared? What's the substitution? A tan theta. What's A tan theta? That's your x, but for us it's the u. So I'm going to replace u with A tan theta. Got it? Got it? I'm using What am I using? I'm using my trig subs right here. I'm using this, right? And I'm using the fact that I have the second one there, right? The second one, except I have I have u squared instead of x squared. So I'm going to make my trig sub u is equal to a tan theta. Once I do this, then I differentiate, right? Take derivative of this. Du would be a secant squared theta d theta. And then we have to figure out what is the square root of u squared plus a squared become. So that's square root of, let's see, u is this, right? So that squared, a squared tan squared theta plus a squared. So all I've done here is rewritten this, right? Any questions so far? Everyone's okay? What do I do here?
Factor out the A.
Take a squared out, factor a squared out. So I factor a squared out. I'm left with, in parentheses, tan squared theta plus 1. But that's the Pythagorean identity, right? That's secant squared theta. So this is square root of a squared secant squared theta. And because I have multiplication between these two, I can take the square root of each one individually, right? So that's a secant theta. All right, that's it. That's all the setup, right? Every time we do a trig sub, we write down what the trig sub is, we take the derivative of it, and then we figure out what the square root part's going to turn into. And now we just go and rewrite the integral. So this integral will become 1 over, okay, the square root, all this, right? The square root part is this, right? Which is that. So that is going to replace with a secant theta, but then I still have to square it, don't I? So can I square it right now? Just write it. So it's a squared secant squared theta times the du, right? This is the part, don't forget, you need the du in here, and du is a secant squared theta d theta, right? A secant squared theta d theta. And this is nice, huh? The secant squareds cancel, and one of the a's cancels, not both of them, right? Just one. See, right, on this derivative, the a is not squared. So this secant squared goes, that secant squared goes, one of the a's goes. All right, so what's left? 1 over a, right? 1 over a, which is a constant, I can pull that out. Integral, now what's still in here? Just 1 d theta, right? 1 d theta. That's it. Any questions? We're not done, but we're good? What's the antiderivative of 1? Theta in this case, because we've switched to the variable to theta, right? So the antiderivative of this would be 1 over a times theta plus a constant. We need to know what theta is, right? What's theta? We need it in terms of u. So we come back over here, right, to our trig sub, where we made our trig sub. This is it right here. And we can solve that for tangent theta. If I solve that for tangent theta, I get tangent theta is what, u over a? I'm doing that because I'm about to solve for theta. How do I kill off the tangent? Inverse tangent, right? Arctangent. So I'm going to take inverse tangent on the left, inverse tangent on the right. Right? This side becomes theta, is that. And I stick it right into that formula. Right? This is what theta is. So this becomes 1 over a, inverse tangent of u over a plus c. That little box means I've shown you what I wanted to show you. All right? Yes?
Why did you choose tangent?
To solve for theta here, why did I choose tangent? Because this is where I made my trig sub, right?
Yes.
So I can solve for theta here in terms of u.
Right.
So I use this equation. I did not need to draw a reference triangle. The reason I didn't need to draw a reference triangle is because at the end right here, this was not a trig function. This wasn't like sine theta or cosine theta. If it was, then I would have drawn a reference triangle. But because it's just theta, I'm just going to use this and solve for theta. Make sense? So do you see we've shown this formula? We've shown that this is a formula, right, that we can use now. I want you to do that for that quiz, all right? For what? How many are there? 4 of them? Yeah. All right. Can we move on? No questions? You sure? All right. Okay, so now we're going to start talking about things that we need to be able to do in order to be successful in this section. And there's 8 problems we're going to do today. And when you look at these 8 problems, they all are going to have a form to them that I want you to be comfortable with. So look at this first one. These problems are not, this first one's not meant to be hard or tricky or anything like that. Okay, this first problem here, we want to be able to find, we want to be very comfortable finding the antiderivative of something like this. So when you look at that, I have to the side there that this is a constant over something that's linear in our variable. So do you all agree that the numerator is a constant? Do you agree that the denominator is a linear expression in x? Yes? Okay, so whenever we have a constant over a linear expression in x, we could always, in every integral we'd ever have that looks like this, couldn't we always just make a basic u substitution? Basic u sub, right? And then the derivative of this in this case would just be dx, right? Or 1 dx. And then I could rewrite this as, let's see, that 2 on top, can we just pull that out?
Yes.
And then 1 over, what does this become? X minus 4 is u, right? And dx was du. Right, that's just our basic u sub. And then what's the antiderivative of that? 2 natural log absolute value of u, right? So what's u? X minus 4 plus c. So what we want to see here is that if you ever have constant over linear, it's a basic u sub and it should be pretty fast, right? Yeah. So fast, in fact, that we don't even want to, from here on out, we don't even want to have to write anything down. So look at the next problem. Is that a constant over linear? Yes. Yeah. Okay, so if you have a constant over linear, right? If you have a constant over linear, you know that you can make u the denominator, right? In this case, what would du be? So we know u would be this, right? Or u would be the 4 minus 5x. What would your derivative be? Negative 5 dx, right? And you don't have a negative 5 here, do you? So you'd have to scale it, wouldn't you? Okay, so can we go straight to an answer without having to actually write all that stuff down? Anyone want to tell me what it would be? Negative 1/5. Natural log absolute value. 4 minus 5x plus c. Perfect. So look, the bottom is u, right? So this looks like 1 over u. The antiderivative of 1 over u is natural log of that. So that explains that part, right? Yeah. But if you were to take the derivative of this, because of chain rule, you have to take derivative of that, and that would give you a negative 5. You don't want that there, so you kill it off, right? That's what's going on there. Let me give you another one. I think our third example is something different. Hold on. Yeah. I'm going to put like 3 of them up here, and let's see how fast you can get these. So what if we did 4 over 3x minus 7 dx? How about negative 9 over 5 minus pi x dx? How about 1 over, I don't know, all 3 of these are a constant over linear, right? Yeah. All 3 of them. So right away, you're thinking natural log. right? Natural log. Basic U substitution. U would always be the denominators in these, right? That's what U would be. So this one, the 4 on top, I'm just going to bring it out. I know that the antiderivative of this, 1 over this, is going to be natural log of 3x minus 7 plus c, right? But what am I missing out front? A 1/3 to kill off the 3 that would come out of this with chain rule. So I need 1/3 here. So this would be 4/3 natural log, absolute value, 3x minus 7 plus c. Who wants the next one? Good?
9 over pi.
9 over pi, natural log of 5 minus pi x plus c. Okay, so pi is just a number, right? I was trying to throw you off here. 5 minus a number in front of x. This is still a linear expression. The negative 9 comes out, right? So that was a negative 9 times. Now we had to scale out by 1 over, but this is a negative, right? When you take derivative of this, you get negative pi. So you have to scale by 1 over negative pi, and that's why we have positive over, well, negative over negative would give us positive here. Understand? Last one?
Negative 1/3.
Negative 1/3. Natural log 4 minus 3x. Okay. Constant over linear should be quick, right? Okay, let's look at the next thing. What about a constant? Why is that over there like that? What about a constant over a repeated linear factor? So let's go back to this one. I'll do that one in a second. Let's go back to this one. This is a constant over linear, right?
Yeah.
What would happen if instead of the denominator being a linear expression, it's a repeated linear expression, meaning this was x minus 4 maybe to the 5th power. Do you see what I mean by repeated? Linear factor repeated. So this is really x minus 4 times x minus 4 times x minus 4, 5 of them. How does it change our problem? Do we still use the same substitution?
Yeah.
Yes. What happens here?
You bring the exponent in.
This will be u to the what? 5th power, right? And we no longer have natural log. Do y'all see that? Natural log is only 1 over u. That's when you get natural log. But if you have 1 over u squared or 1 over u cubed or 1 over u to the 4th or the 5th, it's no more natural log, right? So what would change is that this would now become 2 integral. I bring that power up, u to the negative 5, right? du. Then I would use my power rule. So now I'm ready for my antiderivative. I add 1 to this, right? And I have to also scale by that, don't I?
Yes.
So negative 1/4 out front, u to the negative 4 plus c. Right? And these two to come together, negative 1/2. U was x minus 4 to the negative 4th power plus c. I could leave it like that, couldn't I?
Yeah.
Or I could drop it down if I wanted to. Negative 1/2. I could put it down there with the 2, like this, x minus 4 to the 4th plus c. That kind of looks weird. Maybe put the negative 1 up here like this. Yes?
So what did you call this, a repeating what?
Repeated linear factor. This is a linear factor that's being repeated. This constant over single linear factor, pretty straightforward, I think. Constant over repeated linear factor, still straightforward, but a little bit more we have to worry about, right? Let's try that one right there. The goal is to try and be able to do that without writing a whole bunch of stuff down. Okay, like you want to try and get to a point where maybe you can do that in your head. If you can't, you have to write everything down, that's fine. It's just that starts taking you a lot more time, right? You're taking a test and you're having to do each of these by hand. It's going to start eating up your time. So let's look at this number 3. Integral, let's see, 1 over 2x plus 1 squared dx. All right, so I look at that. As soon as I look at it, I see I have a constant over a linear factor that's repeated, right? So I'm going to make a basic u substitution. U is going to be what's here. What will I have to scale by? A half, right? Where are you getting? Oh, you're already doing that. I'm just saying in terms of this 2, in terms of the 2, I'm going to need a half, won't I? Okay, so how do y'all want to do this? I'll show the steps, okay? I'll show the steps, but this is what we're doing. That, right? Du is 2 dx, and so I have to scale by a half to get dx, okay? So that's my basic u sub. I rewrite the integral as, let's see, integral 1 over, this is u squared, dx is 1/2 du, so I bring the 1/2 out the front. This is really u to what power? Negative 2. So this is half integral u to the negative 2 du. And now the antiderivative of u to the negative 2 is negative u to the negative 1. So 1/2 times, I'll write it this way, 1 over negative 1 u to the negative 1 plus c. Power rule on this, right? You add 1 to the power, you do 1 over that power out here. So I think I'm ready for a final answer, if y'all are okay with that. I'm going to put this together, so negative 1/2. And then,
1 over.
yeah, however you want to do this, right? I'll write 2x plus 1 to the negative 1 plus c. And of course, you could always drop that down. All I did there was just replace the u. Can we do one more? Yes.
When you dropped it down, would it just be 2x plus 1, but on the bottom?
On the bottom with the 2, and there would be a 2 in front of it with parentheses around the 2x plus 1. You could distribute that 2 through the bottom. Yep. What about this? How about 5 over 3 minus x to the 7th power dx? Okay. I look at it, right? It's linear over repeated, I'm sorry, constant, I just said that wrong. It's a constant over a repeated linear factor, right? Okay, so first thing I'm going to do is see that 5 up top? I'm just going to bring it out. I'm going straight to my answer right now. 5 times, okay. I'm going to need to scale by what to take care of when I do the derivative of this? I need a negative 1, right, to scale it? Okay, times. Now, when I do all that, I'm seeing in my mind that this integral is really turning out to be like 1 over u to the 7th, right? Something like that, which is really like u to the negative 7. The antiderivative of that is 6u to the 6. That, right? Do you all understand what I'm doing there?
Yeah.
Okay, so, oops, sorry. Okay, so now what's u? U is 3 minus x, and then raise that to the, I forgot the 1/6, sorry. So I need this right here. So times negative 1/6, u to the, u is 3 minus x to the negative 6 power plus c. Yeah, so again, the 5 came out. I need to scale by this negative 1. When I take derivative, I need to scale it, and then that thing's really u to the negative 7. There's the antiderivative, right? Put it all together, 5/6, 3 minus x to the negative 6 plus c. I'm going to check it carefully, right? Let's check it. It should be easy to check, right? Take derivative of this. This comes out, right? And when that comes out, what does this become? Negative 5. Times, now when I took that out, right, the power, I subtract 1, so that becomes negative 7. So 3 minus x to the negative 7, and then times, now the derivative of what's inside, which is negative 1. And when you put that together, you get 5, 3 minus x to the negative 7, and if you drop this down, you get this. right? Questions? Constant over linear. No, I already erased them. Constant over linear, pretty straightforward, right? Constant over linear is going to give you a natural log. Constant over repeated linear, you're going to have some powers and stuff. You got to keep track of some of this stuff, but it can be done, right? It shouldn't take us like 30 minutes to do that problem. We keep going. I've already done something like that. Okay, now, what if you have a constant over a quadratic where your quadratic is missing the x term? So this is a constant over a quadratic that has no x term. Has x squared and it has a constant, right? But it doesn't have the x term in the center. Like if we had it in descending order, right? So how do we do that? Anyone recognize how we can do that?
Plus the x minus 3.
Trig? The square root, like we did to start class, right? No, because this is not subtraction. If this was a minus, then it would be plus 3 minus 3. Then we could do difference of squares.
We still do it U sub and U scale by 2 instead of 1.
U sub won't work because if we do U sub, the derivative of this would be 2x, wouldn't it? And we don't have a 2x anywhere. What did I start class with today? No, not the quiz, but first thing I did. Yeah, so I verified a formula, didn't I? Formula number 17. We can use formula number 17 here. See? Our formula 17 says this. Integral 1 over, now we have it backwards, don't we? On our formula it was u squared plus a squared du. That was the formula I just verified for you. That's what we have, don't we? Oh wait, yeah, it is the right way, isn't it? Sorry, it is the right way. We have our variable squared plus our constant squared. So we go straight to the formula right here. Here for us, u is x and a is what? 3. So according to formula 17, the answer is, without any work, 1/3, 1 over a, arctangent of u over a, right? What's u for us? Nope, careful. U is x. So x over, not 9, careful, a is 3. Remember, this number right here is a squared, okay? That's a squared, so a is 3. So look at your formula, it's 1 over a arctangent of u over a. And we are done, okay? Look, that's the whole reason I want you to verify these formulas, is that once you verified them, you don't have to do this you don't have to do the trig stuff for each of these problems. You just do the formula, all right? But I want you to see where they come from. At least some of them, not all of them. So that's pretty straightforward, right? Let's try another one. What if you had this one? I'm going to see if I can mess you up a little bit here. 1 over 3 plus x squared dx. This isn't much harder, but I'm building up to something here. What do we have? Look at the form. Constant over a quadratic. The quadratic is missing the x term, right?
A is going to be
Yeah, so we can still use this, can't we? Yes. But what's a for us this time? The square root of 3, right? Because this right here is a squared, right? Which means a is the square root of 3. So I'm going to go straight to the formula. 1 over root 3 inverse tangent of x over root 3 plus c. You don't need to rationalize denominators, just leave them. That's fine. Okay? Do another one. Careful. What's that? Yeah, we don't want this 4 here. See, this formula, it's explicitly a 1 here, all right? There's a 1 here in front of this variable. Ours doesn't have a 1, right? It has a 4. So we're going to pull a 4 out of the bottom. I'm also going to pull that 5 out of the top. 5/4 integral 1 over, okay, if you factor a 4 out of this, you get what? X squared. If you factor a 4 out of this, you get 1/4. Do you see now it looks like that formula? Y'all agree that if 4 goes through here and here, you get back that, right?
Yep.
And the 5 comes out the top. Now I can use the formula. 5/4 times, what's a for us here? Be careful, what's a? 1/2, right? The square root of that number. So that's a squared, and that means a is 1/2. So this will be 1/2, wait, no. It's 1 over, let me write it 1 over 1/2. Okay, that's 1 over a, arctangent of u, but u for us is x over a, which is 1/2, plus c. Any questions on where I got the 1/2 from? We're good? Well, let me clean this up. Let's see. This really is a 2, right? And then 2 over 4, that gives me 5/2 out here. Inverse tangent of, now here if you have something over a fraction, you can reciprocate it, and that just becomes 2x, doesn't it? That should be it. We could check our work. Yes?
Wouldn't it be 2 over
2. No, because this right here, right? This is up here if you look at the x like that, and then if you flip it, it becomes, okay. All right, what about this? -9. Okay, our formula does not have plus, does it? It has minus. However, look at your other formulas. Is there another formula there?
Yeah.
Is it formula 19? Make this a little bigger. That looks like formula 20, doesn't it? Variable squared minus a squared. That's formula 20. What's a for us? So using formula number 20, with a being 3, right? With a being 3, I'm going to do 1 over 2 times 3, right? And then fill in that. So 1 over 6, 1 over 2 times 3, natural log, and then u minus a, x minus 3 over x plus 3 plus c, using formula 20. What if I had given you the problem backwards? What if I had given you 1 over 9 minus x squared dx? What then? You could use formula 19, right? Or couldn't you pull a negative out of the bottom? If you pull a negative out of the bottom and bring it out, wouldn't it become a -1 out here? So couldn't I